Okay, so last but not least, for conservation of mass, we're going to cover our quiz, not quiz. Remember, these are problems that are, I guess we call them meaty, so that you can do them with groups of people and sit and talk about it and debate about it, which is great. And we are going to do this in a video, but if you're planning on attending class, then I would not watch the video and do this in class, so we can do engaged learning in class, right? Where you are discussing it with people, and that's where you really do a lot of learning. Okay, so let's assume May isn't really, let's assume this is a hot tub, not just a tub, but a hot tub. Hot tub in the back of a limousine. And it's graduating, and you and your friends have rented a hot tub limousine, and you're traveling around Buffalo. And because it's spring, it's raining. So we want to know how much rain accumulates after driving around for an hour, because that is all you guys could afford, because you're still not working at your jobs yet. You have them, but you're not working at them yet. So what are the parameters for this? It's raining. The velocity of the rain is 10 meters per second. That is an accurate velocity for rain, like a typical rain falling. The density of the rain, if you average it out, not the individual droplets, but averaged out, is 7 times 10 to the negative fourth kilograms per meter cubed. That is also accurate. You're welcome. That's actually, by the way, a great thing to break out over Thanksgiving. You know, you're at the dinner table. It's really awkward, and you're like, do you guys know the density of rain is about 1 times 10 to the negative third kilogram per meter cubed? It's about 1 millionth the density of water. That'll go over real well. Okay. So and your car is traveling at 10 meters per second. We want to know how much, like I said, rain accumulates after driving around for an hour. And if we're looking for accumulation of mass, we have some velocities, we have some areas. It should naturally come up that we want to use the conservation of mass model. So I have written it over here on the right-hand side. Right here we have d dt of rho dv is equal to the integral over the control surface of rho w dotted into n hat dA. Remember, w is the velocity of the rain relative to our control volume. So we have which part of conservation of mass, so let's go through these questions. Which part of conservation of mass is changing of mass with time within the CV? All right, because that's what our question is asking, is how much rain is accumulating after driving around for an hour. So if that is the case, that's this right here. This is m dot of our CV. That's our change of mass with time. All right, so let's draw our control volume now. And if we wanted to get clever, remember I told you when we were talking about ways of simplifying your control volume, that you should almost always choose it to be your control volume to be perpendicular to the flow, the surface. But here is one case where I would not. I would draw it right here, because if you draw it perpendicular to the surface, it gets tricky figuring out what the area of the entrance is, because then you have to project the entrance. We're just going to draw it right around our tub, and that way we know that the area here is 2 meters squared. So there's our control volume. We've done that. Is it pinned to anything? Yes. We're going to pin it to the car. Now, pinning a control volume just means that it's moving along with the car. So our control volume now has a velocity of 10 meters per second. So now what we need to do is we need to figure out what the velocity of the rain is relative to the CV, i.e. find W. Oh. Looks like I did not erase that before. Okay, so if we're going to find W, we can do that. So velocity of our rain, V rain, is equal to 0 I hat minus 10, what did I say it was? 10 meters per second? Yep. Minus 10 meters per second J hat. So now you notice we have an Eulerian description of our velocity, but we also have units now, which is great. And so we have to do it relative to our CV, which basically means we just subtract the velocity of our CV. So W is equal to V rain minus V CV, which is equal to negative 10 meters per second I hat minus 10 meters per second J hat. And now we should double check that to make sure that makes sense. So we're sitting here on our CV, literally sitting in our hot tub, and our car is driving to the right, and we have positive X to the right, we have a positive Y upwards, and if we're sitting here facing forward, the rain will appear as though the rain is coming down like this, which would be a negative X direction and a negative Y direction, which is exactly what we have. And it's great to do those kind of sanity checks on an exam. So, what is W dot N hat? Well, W dot N hat we have, is fluid entering our CV? Yes, it is. It's coming in here at an angle through our CV and filling our tub with cold water as opposed to the hot water that's already in there, which sucks. And it's going to be negative 10 because it's negative because it's entering and it's 10 meters per second. But let's figure out why it's 10 meters per second. We can't just do our normal rule where it's positive or negative the velocity, because it's entering in at an angle to our control volume, not parallel to the unit normal. Our unit normal is coming off like this, right? So our unit normal is 1J. So our N hat is equal to 0 I hat plus 1 J hat. And we know what our W is, so if we do if we dot that in, we're going to see that our W dotted N hat is equal to negative 10 meters per second I hat minus 10 meters per second J hat dotted into 0 I hat plus 1 J hat. And if we do that dot product, we get negative 10 meters per second times positive 1, which gives us a negative 10 meters per second. Great. So we've done that. What is m dot total? Well, we're going to, wow, I really didn't erase everything here. What is m dot total? Well, we're going to make some assumptions here. Assume rho is equal to a constant. We're going to assume uniform flow, right, which is basically saying that our rain is going to have a uniform velocity as it enters our control volume. And then we're going to assume a steady state. In other words, we're just driving down the road at 10 meters per second. Maybe we're on 33 and we're just cruising. We're steady state. Oh, we're not steady state, though. Our flow is not changing with time, but we're not steady state because we're accumulating mass. So let's write out our conservation of mass equation, which is 0 is equal to the integral of our control volume of rho dv d dt of that plus integral over control surface of rho w dot n hat dA. We know this. We just did the work for that. We know this is a constant. We know it though. And this is what we're solving for. Remember, this is m dot total. So m dot total, 0 is equal to m dot total plus, we don't have to do the integral, right? Because we assumed uniform flow. So we have our density of our rain times a negative 10 meters per second for our W dot N hat times our area, which is 2 meters squared. And remember, this is equal to 7 times 10 to the negative 4th kilograms per meter cubed. So we can plug all this in, and we find out that our m dot is equal to I don't have that written down, so we're going to have to do our calculator. Go ahead and bring out your calculator and try it too in order to try to beat me to it. We have 7 times 10, clear, 7 times 10 to the negative 4th times 10 meters per second times 2 gives us 1.4 times 10 to the negative second. 1.4 times 10 to the negative second kilograms per second, right? And remember, the negative drops out because this comes over to the other side and it cancels out our negative because we have negatives on both sides. So that's great. It's positive. It makes sense. The rate of accumulation is not that great. So if we're driving around for an hour, what is our total amount of mass accumulated? Well, this is a constant. M dot's a constant, so our M total is just equal to M dot total times delta T, which is equal to 1.4 times 10 to the negative second kilograms per second times 3,600 seconds, which gives us apparently 50.4 kilograms. We're going to double check that though. 1.4 times 10 to the negative second times 3,600. Yep, 50.4 kilograms. So you gain about the weight of a person, a light person, but a person after driving around for an hour in this medium rain. Cool. And that's a conservation of mass.